STAT340 Exploring Data Part 3. So, this module we will have a look at clustering of data, and first of all the motivation for doing this, some motivation at least. And then groups in data distances, because whenever we are going to group our data we have to decide what we mean by similarity, right? And distance is the opposite of similarity, right? Lack of similarity, that's distance. And this is not as obvious as you may think. And we will have a look at some alternatives here. The Minkowski distances and some other, well, not too uncommonly used metrics, as we call them. And then we will look at one method or algorithm for doing clustering, grouping of data. And that's the hierarchical clustering. The algorithm itself we will explain, it's fairly simple. And also the result we display, the dendrograms. And we will also look at another completely sort of different approach to clustering, and that's partitioning. The most commonly used is the k-means algorithm. We will have a look at that. But an alternative, which is almost the same, is this PAM, or partitioning around medoids. So we also mention this because it has some facets that this one up here lacks, you could say. We will see that. And finally, we will also have a look at how can we actually determine how many groups are there in our data. And this is pretty sort of important in some cases. But we should also stress that since this is still exploratory, we are not sort of always too hung up on this. But in some cases, it's very nice to know how many groups do the data themselves actually support. We may sort of think that we see some patterns, but this is actually supported by the data. Yeah, gap statistic is one approach to evaluate this, you could say. So that we will have a brief look into. So clustering methods is mostly found in chapter 25 in the R book, same as PCA. So this is sort of related to PCA in the sense that it's treated in the same chapter, but otherwise not so much, I would say. But they are both ways of exploring data. That's true. So the motivation, and of course it's explorative, right? This is a way to inspect large data sets as well, just as PCA was a way to sort of take a sort of graphical inspection of the data. This is an alternative approach. Can we actually see some patterns in this data without plotting, you could say? Can these clustering algorithms find groups for us? And patterns is usually the same as groups, right? We may get some hypotheses or ideas about our data from such an analysis, but it's never conclusive, right? You cannot conclude anything based on the clustering, I would say. It just is an indicator of something. Just as with PCA, this may also reveal outliers or severe errors. So that's important, right? You typically then, if you have an outlier, this data case ends up as a group on its own, right? So if you end up with groups having very few data points or a single data point, right? Then you should be sort of a little bit skeptical and investigate that further, because it's then very different from the rest, right? That's what it means. I would also like to mention downsampling, which is something you may not have heard about, but this is what it means is that if you have collected a vast number of data, and that isn't so unusual in our days, where we have tools, or should I say technology, to collect a huge amount of data. But not all of this data are really sort of essential in a sense. Then you can downsample and And without losing almost any information, you can replace the full huge data set with a much smaller data set. And clustering is also one approach to doing that. In some sense, similar to what we did with PCA, right, where we replaced a huge number of variables with only a few sort of principal component variables. In this case, we talk about the rows instead, the data cases, right? If you have a huge number of data cases, many of them are almost identical, right? And then you can replace this by just selecting the cluster representative, you can say. Group them and select one from each group as a data case. So the cluster center typically in some way represents then this region of the data space. Yeah. So groups in data. Oops. A data set has n data cases and p variables, right? And here they are. We have seen this before, right? We arrange it in table like this, where we have p columns and n rows. And I call it x11 to x1p here, xn1 to xnp here then. Right? So we have just some indexes indicating which row and column we are in. When we look for groups in the data, we look for similarity between data cases. So data cases, that means rows, in the same group are in some sense similar to each other. And data cases in different groups are then different from each other in the same sense. So notice that it's always the rows that we cluster. Always. This is by convention. The data cases are clustered. In case you wanted to look for groups in your variables, I mean that's legal because this is exploratory, so you can do whatever you like. Just transpose the data table. Flip it around so that rows become columns and vice versa. And then you do the clustering on those rows, you could say, which are then the original columns. So that's legal. But and since that's legal, we say that given the data table, we always cluster the rows. That makes it so much simpler here. We remember when we talked about PCA that each case here now, each row here can now be seen as a point in a p-dimensional space. And why p? Yeah, because we have p coordinates, right? P variables. Each number here in a row is a new coordinate along a new axis. So they are points. And grouping of the data means we have to choose what we call a distance metric now. That says something about the distance between two such points. What do we actually mean by distance between 2 points, between 2 rows here? And that's what we are going to look at now. Minkowski distance. What is this? This is a general formula for distances between 2 data cases, and it looks something like this. So here we have the first data case. Here we have the second one. I just call them like this now, xi, xj. And notice both have, of course, p coordinates, right? They are 2 rows in the same table. And then the general Minkowski distance formula looks like this. So here, this is just an expression for the distance between these 2 rows. And look at what we are doing inside here. First of all, this summation here goes over the columns, right? Because it starts with k equals 1 to p. So we jump from column to column to column. And what do we do for each column? Yeah, we take the coordinate for xi minus the coordinate for xj, and then we take the absolute value of that. So it doesn't really matter which one is first or last of these 2. And then we take it to the power of q. Power of q, right? Before we sum. So actually we go from column to column compare the two coordinates in that column. Look in the two rows, right? Compute how different they are and the power of q of this. And then we go to the next one and add this up for all columns. And when we have done that, we take then the q root. So it's the same q here as here, right? So we take the q root again of this. And this is because we did the q power inside here, right? So this is the general Minkowski formula, you could say. So how do we choose the value q here? Well, with q equal to 1, this is called the Manhattan distance. And what does it mean? It means that q equals 1 here means you to the power of 1. Yeah, okay, that's not doing anything at all, actually, right? So you just list the absolute differences and sum them up. And the sort of the 1 root means you do nothing here either, right? So it's simply a summation of these absolute differences. If you choose q equals 2, you get what we call the Euclidean distance. And this is actually the distance we normally think of as a distance between 2 points. The Euclidean distance. That's when q equals 2. Because then we take the square here, right? Then q becomes 2. The square deviations, then you actually don't need the absolute values anymore, but because squares are always positive anyway. But it doesn't matter if they are there, right? So you sum up the square differences, and then you take the square root at the end of the summation. Then you get the Euclidean distance. But you can choose also bigger q values, 3, 4, and so on. But these two are the most commonly used, q equals 1 or q equals 2. But the general Minkowski formula looks like this then. When q grows and gets bigger than 2 or much bigger than 2, you put more and more emphasis on the largest coordinate difference. So actually, if you think of sort of q growing to infinity, that has a name of its own, and that's called the maximum distance. It's a strange name because it's not the biggest distance possible. It's maximum because then you look for the maximum of the coordinate differences. So the distance between two rows is simply the distance between the two most different columns. You find the column with the biggest differences, and that's the difference between the rows. You ignore all the other columns, you could say. Only look at the column with the biggest differences. But that's not so commonly used. It's these two that we use quite a lot. Let's look at an example here. And here I have chosen now 3 sort of rows, right? And here we have 2 columns, so we have only 2 coordinates. And that's because I want to plot it. That's why I have only 2 coordinates now. So the first one is 1.0, 1.0. Second one is 2.0, 1.0. And the third one is 1.6, 1.6. Okay, so this could be easily numbers, right? We have in our data table. If we plot this now, and we call this coordinate here, we have 2 axes here now, right? This is the first and this is the second axis. Then we will have x1, this is positioned here. x2 is positioned over here, and x3 positioned over here. So now it means that this here is 1, here is 2, and here is 1.6, right? 1, 1.6, 2. And if you go to the second coordinate, x1 has 1 here, x2 is also 1, but this one is 1.6. So the Manhattan distances between these points, how are they actually computed? Well, here is the formula for computing the distance between x1 and x3. The Manhattan distance between these 2 points. And it's now like this, right? We start in the first column, look at the absolute differences to the power of 1, and then the 1 root, which means we can just skip that Q altogether since it's 1. And then we go to the second column and do the same thing here. Look at the absolute difference. So this is 0.6 and this is also 0.6 and added together 1.2. That's the Manhattan distance here. And this is how we actually compute it. Did you notice, follow this path. We first compute the distance along this axis. That's this one, right? And then we computed, here, and then the difference along the second axis, this one here, and add them together. So actually, the distance between x1 and x2 is the length of the path, you could say, that you have to walk if you walk first along the one axis and then along the second axis. And this is exactly the Manhattan distance sort of property, that you have to walk along each of the axes one by one. And that's also why it's called Manhattan distance, because if you are in a grid, if you're in a city, you have to, when you're walking from sort of one corner to another corner, you cannot walk in a straight line through the walls of the buildings, right? You have to follow the roads, the streets. And on Manhattan, it's streets and avenues, right? So it's actually the length you have to walk when you are sort of trapped inside a grid of a city. If we look at the second distance here between x1 and x2, the same formula, of course, and the distance, and now we just have to walk along this street here, straightforward, right? So it's actually shorter. It's shorter between x1 and x2 than it was from x1 to x3. You can see that 1 instead of 1.2. If we compare this to the Euclidean distances, and what are Euclidean distances? Here's the formula then. And now we take the same difference now, between x1 and x2, yeah, the last one we started with here. We take the differences again, but now we square them, right? And then we sum them and we take the square root. And again, we have actually the same distance as we got from the Manhattan distance. And that is because we actually have only a straight line like this. But when we compute the distance between x1 and x3, now you will see, yeah, here it's marked by this thick red. If we do the same for x1 and x3, we will see a smaller distance. Notice how the Euclidean distance is now much smaller than the Manhattan distance was. And that is because this is now the length of the straight line between these 2 points. And why? How can I say that this is the length of the straight line? Well, this is simply Pythagoras formula, right? You say that this part here is this one squared, right? Plus this one here is this one squared. And we know that if you take this one squared plus this one squared, you get this one squared. That's Pythagoras. And since we then take the square root, this is actually the length of that straight line. So notice how dissimilarity or distance between 2 points varies slightly sometimes, depending on how you measure distance. So if we measured by Manhattan distance, we would say that x1 and x2 are the ones who are closest to each other. x3 is farther away. But if we change to this way of measuring distance, it's actually x1 and x3 that's closest to each other. And this one is further away. So it's not irrelevant. The way you choose your distance metrics has some impact on the outcome of this. So make up your mind, how should I measure distances now? Okay, let's have a look at some other distance metrics that are sometimes used, at least here at NMBU. The Bray-Curtis metric, what is this? It's used in ecology, and here it's not typically referred to as a distance, but what is called a beta diversity. But we can think of it as a distance. It actually reflects the distance in species composition between sites. But of course you may in principle use this on any data, but this is where it comes from. And let's have a brief look at what it means here. So let's assume we have a data table like this. We have collected data for 3 species. And what are the data? Well, we have sort of visited 2 sites, let's say 2 different forests. And we went into this forest and collected how many times do we see species 1, species 2, and species 3 in this forest, right? This is something that ecologists sometimes do, right? And then you go to a second forest and you do exactly the same thing. You go looking for the same 3 species and count how often do you see them as a sort of a measure of how common these species are at these 2 different sites. And now we are interested in how different are these 2 forests, right? These 2 sites with respect to species composition. And here is the formula we can use then for the Bray-Curtis dissimilarity. And I tried to put it into a more mathematical language here compared to what you see if you go to the internet and search for this. You will also find a lot about Bray-Curtis in a simpler sort of language perhaps, but this is, I think, the precise statement. So what do we actually do? First, let's look at these denominators here, because these are simply, this one is simply the sum of the values in the row xi, and this is simply the sum of the values in xj. So you sum up what is the sum of the values in both rows, right? In this case it's 17, and in this case it's 16. So 17 plus 16, as seen here. What is in the numerator? Well, again, notice we go across the columns, like we did for the Minkowski, from first column to the last column, column by column by column. But now, instead of looking at the differences, you just sum up the smallest value. That's what this means. Take the minimum of the 2. So you start in column here. What is the minimum? 6. And then you go to the second column. What is the minimum? 0. So you have 6 plus 0. Then you go to the third column. What's the minimum? 4. So you have 6 plus 0 plus 4, which is 10. So this is 10, and then you multiply this with 2. So then you would have 20 here, plus, 17 plus 16 is 33. 20 divided by 33, and then 1 minus this. That's the distance between these 2. And notice now, if the values in the 2 rows were identical, exactly identical, the exact same value in both rows, then of course the sum of the rows will be the same. So these 2 will be the same, and they will be exactly identical to this one as well, because the minimum is now the same as one of them, right? So the sum of the minima is the same as the sum of one of the rows. So it's the same value here in this summation as you have in these 2. And since you multiply this by 2, you have exactly the same value, and you have the fraction 1. And 1 minus 1 is 0. So it means that the distance between 2 identical rows becomes 0. You can also see that if there's a 0 in one of the columns here, one of the rows here, and there's a 0 here, and there's a 0 here, then the sum of this here becomes 0. And then the distance becomes 1. So that's the maximum distance you can have in terms of Bray-Curtis. The maximum sort of dissimilarity you can have between 2 sites is 1. That's not all. It's not all distance metrics who has this maximum property, but this one has. Correlation distance is another one which is also used quite a lot, and especially in bioinformatics, I think. And this is just reflecting the lack of correlation. So if you look at the formula, it's horrible. But everything in this fraction here is simply the correlation between 2 rows. Correlation. between two rows. And then you take 1 minus this correlation. So it means that if two rows are correlated, and again, if they are identical, they are also correlated. And then you will have a correlation of 1, and 1 minus 1 is 0. Right? So the distance becomes 0 if the rows are identical. But rows can also be correlated if all the values in one row is sort of a constant times all the values in another row. So this one here does not sort of look at the absolute value of the numbers. It just looks at the pattern of going up and down. So that's what's reflected in this distance measure. We will, I would say that especially this one is very different from the Minkowski distances. The Bray-Curtis is not. So if you measure distance by Euclidean distance, for instance, and then compute the Bray-Curtis, they will not be super different from each other. But this one can be super different from these others. So this one sort of put emphasis on completely different aspect of your data, you could say. And that can sometimes be valuable, right? If you are exploring data, you should try to explore them from many different directions, you could say. And this is a very sort of different way of sort of measuring distance between observations. Okay, let's go to an R session and see how we compute distances in R. So let's look at this R session here, distance metrics. We need some data, and there is a data set in our R package called taxa. Let's have a look at it. And I have made myself a script here, and I have saved it under my STAT340 folder, so that it's available to me. Like that. I want to see that folder. Yeah. Let's source this, and we have this taxa here. What is it? It's a data. Oops. Head. It's a data set of of plants. It's 120 plants. It says n equals 120, where for each plant there has been some measurements of some sort of body parts, you could say, of the plant. Petals, internodes, sepal, bract. Yeah, so these are some measures, lengths, I suppose, of different parts of the plants. And this is typically something we would be interested in clustering, right? To see if there are some sort of groups. Are there some plants who are more similar to each other than others? In terms of how they look like, right? Because this reflects how they look like in not the colors and stuff, but the sizes and proportions. Yeah. So at least it's a data set with 7 p equals 7 here columns. So let's see how we can compute distances between the rows in such a data matrix. And here are some code for this, and there is a function in R called dist that computes distances, and this will typically take then as input the data table. And remember, it always computes the distance between the rows of the data table. So if you wanted to compute the distance between what is now the columns, then you have to transpose your table, right? To flip it around so that rows become columns and columns become rows. And then you use the dist again, and then you get the distances the other way, you could say. But we will look at the distance between, because each row now is a plant, right? So here is how you compute the Euclidean distance. You use the dist function, and then you supply as an option here which distance metric you want to use. Method equals Euclidean, then you get Euclidean distances. And then we see a similar way of computing the Manhattan distance. And this dist function has quite a number of built-in options for computing distances. So use question mark dist like this, to get to the help file, distance matrix computation. Right? And then you scroll down here and look at the arguments, because here you can see method is described. The distance measured to be used must be one of these ones here. You can choose between Euclidean, maximum, Manhattan, Canberra, binary, Minkowski. Yeah. And it's explained a little bit more down here, the details of each one of them. So you can always have a look at this, and I think you should in one of the exercises. But yeah, and then let's compute these two types of distances here now and see what happens. So I run this line and this line, and notice what is the output from this dist function. It's an object called dist. And if we look at it in the console window here, for instance, the D Euclid, it doesn't look very pretty. And how is it actually represented? Yeah, here you can see at the beginning of it. It's represented as, imagine you have a distance matrix, right? Where you have, since we have 120 rows, this becomes quite big. So actually, I think I will, let me make a small distance matrix here, a small data table, sorry, that only contains the first 4 rows of this taxa, right? And then we look at the dist of x instead. Like this. So here you can see that we get the distance between row number 1, 2, and 3 to row number 2, 3, and 4. Because you can also convert this directly or to a distant matrix. And let me show you. You just do it. I do it directly like this here now as matrix. And then we get the full matrix. Full distance matrix, and it always is, if you compute between 4 cases, it's a 4 by 4. In the case with the full data set, we have 120 cases, then we get 120 by 120 distance matrix, right? So each cell here now is the distance between this row and this row, right? And of course, on the diagonal, it's always 0, because the distance from one point to itself is 0, regardless of distance metric. All distance metrics must fulfill this, actually. If it doesn't, it's not really a distance metric. So it's always 0 on the diagonal, and it's also always symmetric. So the distance from 1 to 2 is here, and also from 1 to 2 here. Notice it's the same number, right? And that is why this dist object that you get from the dist function, it doesn't represent all this matrix, because it's sort of waste, right? We know that it's always zeros on the diagonal. We know that whatever you find here, you also find here. Whatever you find here, you always find here, right? It's symmetrical. So it only stores the sort of the lower triangle of this matrix. Can you see that? The lower triangle. These values here in that dist object, but we can convert back and forth to a matrix like this. Okay, let's plot the differences between a Euclidean and the Manhattan distance for the exact same data. And here you can see that they are not identical, but they are also quite similar. So here we have the Euclidean distance, and up here we have the Manhattan distance, and then we see that there are some points. Let's see, if we fix some value at the Euclidean distance, for instance 5, all the points who are distance 5 between them are up here, right? And we see that some of them have a quite small Manhattan distance between them, but some have also quite big Manhattan distance between them, right? So they are not the same, right? These two distances differ, but we can see they are not super different, because it's very, if you are down here in the Euclidean, you are also down here with the Manhattan somewhere, right? And vice versa, if you're up here in the Euclidean distance, you are also typically quite up here in the Manhattan distance. But the cloud has some width, you could say, in both directions here. Okay, let's have a look at that correlation distance that I mentioned. And this one we cannot compute with the dist function because it has no, there was no option for correlation. So we have to compute it sort of ourselves. And then we use the coider function to compute the correlation matrix. And here we have to transpose because the correlation matrix is always the correlation between columns. This coider function in R will always look at the columns instead of the rows. So we have to do this transposing here now to get the correlation between the rows. So this ends up as a 120 times 120 matrix. And then we'd simply take 1 minus all the values in here. And then we convert it to a dist object with this as dist. So then we have a similar object of this kind here. And then if we plot the Euclidean distance against the correlation distances, we can see that this is very different, right? It's still some relation. When you have small Euclidean distances, you cannot have big correlation distances. But on the other hand, if you have large Euclidean distance, you can still have quite small correlation distance, but you can also have very big. So you can see out here, it's really no relation at all between these two. And the fact that everything sort of shrinks towards zero here is natural, right? Because all these distance metrics, if two rows are identical, if it's the exact same numbers in both rows, the difference must be zero, regardless of how you measure it. So everything sort of converged to zero in here, right? That's why when everything is almost zero, they are also quite similar to each other. But for bigger differences, they can be very different, these distance metrics. So the hierarchical clustering. We have computed some distances, and now we want to make groups of them. What is hierarchical clustering? Actually, it builds a hierarchical distance structure, what we call a dendrogram. It looks like a tree-like structure. And we typically then plot this dendrogram to have a look without actually grouping the data. And the grouping we do by sort of cutting this dendrogram, we will see. Yeah, so we cluster into distinct groups by actually cutting this dendrogram at some distance. But first we typically plot the whole dendrogram. What we need now, in addition to the distances between the points that we saw in the previous session, we also need to define distance between clusters. How do we actually measure the distance between groups of points? And that is what we refer to as the linkage function. And here we typically have three choices. We have some others, but these three are the dominating ones. I will show you now. So let's imagine now we have two groups of data. I color them differently even to highlight. But we can see we have some points over here, and we have some other points over here. So we have two groups, right? Two clusters. What is the distance between these groups? Yeah, there are typically three different ways of defining this distance. The first one is what we call the single linkage distance between the groups. And this is simply the distance between the 2 points that are closest to each other, one from each group. Right? So you look for the point here, which is closest to the yellow, and you look for here the one closest to the red, and then you measure the distance between these 2 points. So this single linkage distance reflects how sort of if the groups are sort of touching each other, right? In a sense. That's the single linkage distance. How near are the nearest neighbors between the two groups? The other one is the complete opposite. And it's also for some reason called a complete linkage, where you actually look for the most distant points in each group. And then you measure that distance instead. So that's the sort of the maximum distance from some point here to some point here. While this is the minimum, right? The minimum distance from some point here to some point here. And then, of course, the third one is the average linkage, which is perhaps the most common, but I'm not so sure. I think actually all these three are used quite a lot. But the average distance is then not between a single point over here and a single point over here. It's the average point over here, right? And the average point over here. And what is actually meant? So how is this actually computed? Because there is no sort of average point, is there? No, it's actually computed as the average of all the distances, pairwise distances, between all the members from here to all the members from here. But it's it will be this. It will reflect the average point to the distance from average to average, the center of each cloud, you could say. And which one of these do you choose? Well, it depends a little bit on what you require from your groups, in a sense. The single linkage means that you get bigger groups, in a sense, right? Because and a new point here. Imagine a new point being a member of the red group. A new point will be a member here if it's just near some of the other points, right? So you can have, for instance, up here, there can be a new point up here, which is close to this one, and then it becomes a member of the red. And then there can be another point out here, which is near this one, which is near this one. So you become member of the group if you are similar to something which is similar to something which is similar to the other members in the group, right? So you can have these long branches sort of out from this center of the group, as long as there are points are sort of densely positioned. You can have these long branches out. So the groups become few and big with a single linkage. And actually the members of a group can be quite different from each other if you have many points, right? Because there can be a long way from one end to another end of the group. While the complete linkage is opposite. The complete linkage defines sort of the diameter of the group. Right? It says that you cannot be member of the group unless you are similar to all members of the group. So the complete linkage groups will become very sort of homogeneous in a sense. All members of the same group must be within some distance to all other members of that group. There cannot be any sort of long branches out in various directions. Everything is sort of compact around the center. And then it must be also more groups typically. And then the average is, of course, somewhere between these two extremes. And that is perhaps why it is the most common, because then it's sort of not extreme in either direction. Okay, let's have a look at the hierarchical clustering algorithm. And this is quite simple and something you should actually be able to reproduce, for instance, in an exam. It could be questions referring to this, because this is something you should really, and we will practice it on the exercise as well. So let's use now the complete linkage. And the complete and the single linkage are the easiest one. The average linkage is a more sort of it requires more labor, more work, because you have to compute the averages all the time. It's not sort of more difficult to follow. It just involves more work. But the complete and single linkage are easier because it's only maximum or minimum distances. We will see. So here we have this distance object, right? So I have now I have 5 points here, 5 cases I want to cluster. And now I computed the distance object with some distance metric. And the numbers here are very simple and nice, right? It's for the illustration, this. So we have the distance from point 1 to point 2 is 3 here, right? From 2 to 3 is here, right? 1 to 3 is here, right? And how do we actually start out clustering when we have a distance table like this? Well, the first step is always find the smallest distance. What is the smallest distance? And here we have it, 1. And then we say, okay, case number 1 and 4 is the nearest neighbors. So this is where we start. We now start building the dendrogram. And here we have the distance axis. And the first part of a dendrogram is merging 1 and 4 into one cluster in a sense, one group, right? And then we tie them together like this. And here we have the distance 1, right? That's the distance between 1 and 4. So this is at height 1, we could say. If you imagine height going up here to the left. So when we have done this, we have to recompute the distance table. And here is the recomputed distance table, because now we have object 1 or data case 1 and 4 is no longer separate in the matrix. They are now joined as one cluster, right? So I call it 1.4, meaning that this includes the old data case 1 and data case 4. So this is a new group now, right? Imagine that we started out with everything being a group on their own, you can say, a single data point, right? Each group, there are 5 groups, each consisting of one data point. Now we have 4 groups. 1, 2, 3, and this here, 4 groups. So after the first iteration, we have reduced the number of groups from 5 to 4. And then we have the new distances here. Notice that the distances out here are just copied from up here. From 2 to 3, right? It's the same number. From 3 to 5, it's the same number. They are just copied. The only differences is in this column here, where we have the merged cluster here now. Because now we need to use the linkage function. So what is the distance from this cluster to this object here, this case 2? Well, then we have to go back up here. That's why we need to keep this original distance table to look up into. And remember, we now use complete linkage. So the distance from this cluster here to this cluster here is the largest distance from one member here to one member here. From 1 to 2, the distance is 3. From 4 to 2, the distance is 3. Yeah, okay, so both of them had distance 3 to this case. So the maximum is then 3, right? From this group to this group, which consists of a single object, it's 3. From this group to this one, we have to do the same. From 1 to 3 is here, 5. And from 4 to 3 is here, 6. Okay, so it's the biggest of these two, since it's a complete linkage. So it's 6 here. If we had used a single linkage, it would be the smallest of the two, right? And if we used an average linkage, it's the average of the two. But now it's the maximum, the biggest. And the same for this, from this group to this group, the maximum distance from 1 to 5 is 2. And from 4 to 5 is also 2. So that's why we get this number. And then we start all over again with this distance table and look for where is the smallest distance in this table, and we find it here. So the next step now is to take this data point and add to this group here. So it corresponds to building the next floor, you could say, in the dendrogram. And here we have now the distance 2, right? Between this and this group. And this depends now on the linkage function, right? The first one did not really depend on the linkage function, but because when you have only one point in each group, all the linkages are the same. But now we have a single point against a group of 2 points, so then this will depend on the linkage function. And since we use complete linkage, it's the distance 2 here now. And then we have to recompute the distance table again, because now we merged 5 with this one, right? So now we get this distance table. And notice now we have an even smaller one, right? One dimension or one row and column is lost in each iteration here. It gets smaller and smaller, this. And again, we have to recompute the distances from this group to this group. What is the maximum distance from 1, 4, and 5 to 2? 1 to 2 is 3, 4 to 2 is 3, and 5 to 2 is 5, yeah. So this was the biggest one, right? That's why we have 5 here. And the same for 6 here, while these two are just copied again from up here. Nothing has happened between the distance between 2 and 3. And again, we look for the smallest distance, and now we can see this is the smallest one. So now we should merge 2 and 3 here. And the distance between them is 4. So this is the next step in the algorithm now. And now there is only one step left, because we can now make another distance table, but it becomes only one cell, right? And that's the distance between this group and this group. And what is it? What will it be? Well, what is the maximum distance between one member here and one member up here? We have to go back here and look. 1 to 2, that's actually the biggest distance in the whole distance table, isn't it? This one, 6. Because 3 is member of this group and 4 is the member of the other group. So it must be 6, the last distance here, since we use complete linkage. So that's how we sort of complete the dendrogram, where all the points are now connected in some way, but some with very big distances and some with smaller. And this is how the algorithm works regardless of how big the data set is. And notice that if you have n by n distance matrix, you can imagine, then it's always n minus 1 steps of this algorithm, because it reduces one row and a column each time in the distance table. So it's this is quite fast way of clustering always. The cutting of the tree. So this is not really a clustering, right? Because everything is connected to everything still here. So how do we actually cluster? Well, then we fix a distance and say that, okay, we cut the tree at a given distance. For instance, this here, right? At 3, I suppose. The value 3. We say that, okay, if the linkage distance is more than 3, then they are sort of cut away from each other, the branches of that tree. And then we end up, as we see here, with 3 groups. This is a group on its own. This is a group on its own. And these 3 are together in a group up here. Those who are now sort of linked together form a group. So where should you cut? Well, that depends also on how strict you want to be with your clusters, right? And this should also be, you have to sort of adjust this to the distance metric you used and to the linkage function you used. For instance, this complete linkage now, if you cut at the distance 3, then you can actually guarantee that within a group, no member can be more than 3 in distance from any other member, right? That's if you use a complete linkage, that's something you can get. Not with a single linkage, or not with an average either, actually. But with a complete linkage, it has this nice interpretation that if you cut the tree at a given height, then you are sort of guaranteed that all the members in a cluster are within that diameter, you could say. Okay. You can also cut the tree not at a given height, but at a given number of clusters. Instead of fixing the height, you can say, I want to divide this into 2 groups, for instance, and then we should have cut up here, right? If we want to have 2 groups, because then we will have one branch down here and another branch down here. So that's also possible in when cutting the tree. Instead of specifying a given height, you can specify a given number of clusters. Okay. Let's have a look at this in R, which is super simple, really. So let's have a look at hierarchical clustering in R. And let me copy this chunk of code here. First of all, I load these packages here, the tidyverse and the ggdendro, and that's simply because I want to use it for plotting. You don't need them to do the hierarchical clustering, which is here. This line of code is the only thing that you need to do the clustering itself, the hierarchical clustering. You need a distance object, right? So we need to use one of them we computed up here. We have 3 of them from previously. All of them can be used. So let's use this Euclidean then as input. And then we have to specify if we want the complete or average or single linkage, and there are some other linkages too. Here I chose average, right? You can try different and see how it turns out. Yeah, okay, let's do that. Let's just run load these packages first so that I have done that. I tend to forget that. Let's do the clustering. It's super fast, as you can see. Even if we have like 120 rows here, it takes no time. Because this algorithm that we just saw, it's very sort of, it's what we call a greedy algorithm. It's super fast and only takes n-1 iterations. So let's have a look at the plot here. And here I use this ggdendrogram function. It uses the ggplot facilities to make things look a little bit prettier. There are some simpler way of doing it in R. I can always show you. It doesn't look very nice here now because there are actually a little bit too many plants, too many cases, right? When you have as many as 120 objects, right, along up here, they are sort of, the text become a little bit. And also the name of each plant is we don't have the name, or it's just numbers, right? So the text that appears here are a little bit, yeah, not the best, I would say. But it displays the dendrogram, right? And here we now have the Euclidean distances, right, along this axis here. So now we can see that there are, at the top here, we have the most different ones, right? So it's sort of divides into 2 big sort of splits here. But none of the branches here are very long, right? And that's something to notice, really, because a long branch along this direction here means that there is a grouping, a natural grouping. If these branches are all very short, it means that there are no sort of natural grouping in your data. And here it looks a little bit like that, I would say. It's not a very super clear place to cut the dendrogram here, because we typically cut the dendrogram at places where you have these long branches and long in the same direction as the distance here, right? Because imagine what that means. It means that you have a long way to travel from one group to another group, right? But here there are no long ways to travel. At least it appears like that to me. But this is a dendrogram. And you can actually plot this in there is a simple plot function If you plot the same object like this, I can always do that just to show you. Then it will look like this, and it's you can see here you have the height axis now, and also notice that they don't hang to the same level here, so you can actually specify. I think it's like something like that. Yeah, then you get something similar to the previous one. You cannot rotate it unless you do something like this. Convert this cluster object to something called a dendrogram object, and then I think you can rotate equals true. Now I'm not sure if this was not really. This was not. I should have tested this. I just guessed now. But you can rotate in this mode as well. But actually, I always use this GG Dendro package, so I have forgotten how to do it in a simple way. But at least this display, this is short and nice, right? If you just want to have a quick look at your figure, while this one opens up much more possibilities for adding colors and stuff to your graph and all kinds of modifications. So let's look at the actual clustering, and here we cut the dendrogram tree in two different ways, as I mentioned in my lecture. You can either cut it at a given height, so the function cut tree cuts this dendrogram at either at a given height. If you specify h equals 3.0, it means cut at distance 3, right? Which means here, right? And then it should end up in a number of groups. You can see here 1, 2, 3, 4, 5, 6, 7, 8 groups, I think, if I cut at the 3. Or you can also specify cut at a given number of groups, k equals 5. Then you will be cutting a little bit higher up so that it cuts actually 5 branches. And let's have a look at the output from this one. And what is clust1 now? It's simply a vector of integers. Clust1. And these are the values. And these are what you see above each value is actually the name of the data case. And since these data cases have integers as their names, it becomes a little bit confusing this. But data case number 1 belongs to group 1. Data case 2 also belongs to group 1. Data case 3 also belongs to group 1. Data case 4 belongs to group 2. Right, so this is the grouping now, right? So we can see here that group 1, and here comes group 3. Data case number 10 and 12 is in group 3, and so on. So, and you can see finally you have group 8 down here, right? So there are 8 different groups. We saw that from the dendrogram actually, that this will result in 8 groups. You can actually count how many you have in each case or in each group with this. Let me just, table of clust1. If we just tabulate, as we say, then you count how many are there in each group. 32 members of group 1, 20 members of group 2, 4 members of group 3, 23 in group 4, and so on and so on. Yeah, we can see that also here, right, that some groups, when we cut here at 3, I think the small groups are up here, right, with 4 and 6 members. And 6 members, yeah. You have some pretty small groups then. And these could be outliers in a sense. You should beware. You should now look at this and see if there are some super small groups. Are these very strange data that form a group of their own? And then we typically put this clustering information back into our data table, right? That's quite frequently done, I think, to have it stored along with the original data, so that because the output here is in the same order as the data are in the data table. That's a nice thing about the data table you used for computing the distances. The distances in this dist object is in the same order as the data are originally. The hierarchical clustering will display or keep the results in the exact same order, and the cutting of the tree is also in the exact same order. So you can actually use this directly here to put it into the. So if I just mutate this and look at my taxa table now, you will see we have the original variables, and here we have now added the clustering of these objects. So now we can see which rows are in group number 1, which are in group number 2, which are in group number 3, and so on. So now you could imagine that you could do a PCA here and plot and then color with this information here and see if you can sort of see the groups in the PCA plot. Okay. Partitioning with k-means. So instead of doing hierarchical clustering, we can also cluster by what we call partitioning methods. And the k-means clustering is the most commonly used of these partitioning methods. So what do we mean by partitioning? Well, this time we group the data into a fixed number of clusters. And so you have to select how many clusters do you want. And typically we try out different values here, right? But anyway, fix the k, number of clusters. Then this algorithm is an optimization algorithm that tries to minimize what we call the within cluster variation. And we can write it as a formula like this. And this is the within cluster variation for cluster number k, right? So we have k, capital K different clusters. So small k is now 1, 2, 3 up to capital K. And then we consider all the members of that cluster, and Ck is actually sort of a display of the cluster K then. So Ij means the data cases that belongs to this group, right? And then we simply just sum up the square distances between all the members of that group. And I should immediately add now that the distances used by the k-means algorithm are the Euclidean distances, nothing else. You have no option here really. So you can see that a squared Euclidean distance, that's actually just a sum of square of the differences in coordinates between these two rows, right? And then you sum up all this for all pairs of members in that cluster. So for cluster Ck, it looks like this. And then you do this for each group. And then the optimization problem is to find the clusters, cluster 1, 2, 3 up to, this should have been a capital K here, such that the total sum of within cluster variation is minimized, small as possible, right? So you just sum this over all the K clusters. How do we actually do that? How can we find clusters such that this is minimized? Well, the algorithm is really simple. First, start out by randomly choosing K of the data cases as what we call centroids. And this is actually the cluster centers. So we start by randomly selecting capital K of our data points as cluster centers. Then assign all data cases to a cluster according to which centroid is their nearest. So you are simply assigned to the nearest centroid, each data point. Then once you have done this assignment, you recompute the centroid in each cluster based on the members, and this then becomes sort of the average member in the cluster, right? The average member of the cluster. And this typically changes the location of the centroid a little bit. because we started out by choosing it randomly and then we assign members to it, but these members are not scattered entirely symmetrical around this centroid, right? It's not like they are in a circle around it. So the center of the centroid will now change a little bit depending on their members of the cluster. So you sort of first you sort of do the dictator assignment, right, to each centroid, but then you do a democratic voting. Where should we put the centroid now based on the members, right? And then you simply return to here again and reassign all data cases again, because now the centroids have changed, right? They have moved a little bit. And then you keep iterating between step 2 and 3 until nothing changes anymore. Then you have a candidate for this minimum here. Because then you have the centroids that are sort of in the middle of their cluster, of their clusters. That minimizes this squared Euclidean distance. But be aware, we started out randomly here. This algorithm may converge to a solution that is not really the solution to this one. It doesn't really minimize. It falls into what we call a local minimum, where it stops. So what you should always do when you do k-means clustering, you should always restart this algorithm several times. And there is an option for doing that in the function we will see in R. So you don't really have to do it yourself. You just specify that, restart this a number of times, so that you start out with one random set of centroids and then run this to it stops. Then you compute this value here and store it, right? Then you select new random centroids, run this procedure here till it stops, compute a new value here and see if it improves, right? And then you do it many, many times, and you keep only the smallest sum of squares that you have found among all these restarts. That's your final solution then. We will see that in the exercises. But let's illustrate the algorithm here with a very simple example. First of all, we have only two variables, p equals 2, so we can actually plot things in a plane like this. We have a number of data points here we can see. And now we want to split this into two groups, capital K equals 2. First step, choose randomly 2 points as cluster centers. And I've colored them red and blue now to distinguish between the two groups. So the blue group center is here, the red group center is here. Then step 2, assign all points to a group, depending on where you are closest to the centroid. So this one is red because it's shorter down here than it's up here, a little bit. And all the blue points are up here because they have shorter distance to the blue X than to the red X. Right? So that's how you distinguish red and blue now. But once you have assigned this now, we recompute the centroids. And then you can see they shift a little bit, because this is now sort of the average among the blue-red points. Yeah, it doesn't look very likely to me, but okay. And this is the average of the blue points, right? So it illustrates that this changes a little bit now. And then we go back to step 2 again and reassign. And then some points here change from red to blue, right? And now we recompute the centroids again, and we reassign again, and then 2 points here shifted color again from blue to red. And then the centroids shift again, and then we reassign again, and then 2 more up here change from blue to red. And so it continues now. And as long as things are changing, we keep on jumping around like this. And when nothing changes anymore, we are done. If the new centroid does not change the color of any member, then of course the new centroid again will be the same as the old centroid, and nothing will change anymore. It stops. So this is where the iteration ends then. And then you should go back and restart the whole thing with some 2 other random starts, right? And see if it converges to the same or if it converges to something better, because now the within cluster variation here should be as small as possible. There is another function in R that do almost the same thing, and the reason I mention it now is that I told you that the k-means always uses only the Euclidean distances. But it might be that we would like to use some other distance metric, right? We cannot use the k-means then. Then we can use this one, PAM, partitioning around medoids. So the k-means has sort of hard-coded the Euclidean distances, always uses this. But the PAM function, and this is in a separate package called cluster, it's similar to k-means, but it uses medoids instead of centroids. And what is a medoid? A medoid is a member of the data set. It's not like an average that lies in between. We saw the x's moved sort of in between the data points in the previous example. In this case, the x's move only among the data points. So you choose the data point which is the centroid of the cluster, or sorry, in the center of the cluster, closest to the center of the cluster. That we call a medoid instead of a centroid. So it's the point that has the smallest sum of distances to the other members in the cluster. And the nice thing about this PAM is that you can supply a distance matrix or a distance object instead of the raw data. Because in k-means you have to supply the raw data, and k-means will itself compute the Euclidean distances, while the PAM does not. Or you can do it for PAM as well, but you can also supply a distance object like we did to the hierarchical clustering. Because here the within cluster variation is no longer this distance squared. It's just the sum of distances. And these distances can now be any kind of distance that you supply. Right? So that's the difference. And I think that in many ways this is much more natural, isn't it? If you have sort of decided upon a distance metric, then the variation in the data should also be measured by that distance metric, I would say. So it's a little bit strange to me that this k-means always insists on the Euclidean distances, but this one doesn't. So we can use this one. So it's the same sort of criterion in the sense that you look for the minimization of this again, but now this is computed in a slightly different way. And the algorithm is the same, except that when you recompute instead of recomputing the centroids, you recompute the medoid, right? You see if the center changes from one member to another member in the group. So it has a tendency of converging a little bit faster, this one, but this sum here is not as good as for k-means. If you use Euclidean distance in PAM, you will not get as good or as small minimum value, because the center of the cluster must be one of the members. While in k-means it's sort of the average member, you could say. Okay, we will have a look at how we can do both k-means and PAM in R. Let's see how we can do partitioning in R using k-means and then PAM. So first of all, let me copy this code here into our studio like this. And actually the k-means function is super simple. It's one line of code like this. It's always available in R. You don't need any extra packages. The first input is always the data, the raw data. And now I have to remember that up here I added this extra column to my taxa data, right? So actually if we have a look at that data set now, I should not include this last column here, right? This is actually not part of our data. It's the first 7 columns who are the data, right? So let me, while I remember it, go back here and specify that I should look at only column 1 to 7.
Otherwise, I will also include this column here as a data column, and this will of course affect my results. So that would be silly. So I should keep that out of my data set now. Yeah. So you have to do this. It will still work if you don't, but you will get a result that is also influenced by the cluster. The clustering result from the hierarchical clustering will sort of be a data column. That's silly. Okay, we can do the clustering like this. Zap, it takes virtually no time. And let's have a look at the content of this object here, cls.km. If you click it open like this, you will see that it contains some objects inside, and we will have a look at some of them. The first one is this, the cluster object. And this is the clustering information like we saw with the hierarchical clustering when we cut the dendrogram. So here we have now each data case, right? Data case 1, 2, 3, 4, and so on. And here is the group they belong to. Group number 2, group number 3, 3, 3, group number 1, 1, and 3 again, and so on. So it's the same type of information. A cluster vector, we call it. That with integers indicating if you are belong to group number 1, 2, or 3. We can of course do this table like we did previously just to see how many are in each group. And here we chose 3 groups, right? So we have 3 groups. 53, 39, and 28 members. None of them are particularly small, which is good. It's if you get a super small group and only have 3 groups, then it's probably some outliers or some very deviating data, right? Notice we also use 10 restarts here. Always use more than one, I would say. How many? It's super fast, so you can easily use more than 10, but at least 10 or at least some, right? Okay, that's the clusters. We can also have a look at actually the centers in each cluster. So if we make that window a little bit, yeah, we can do, yeah, that's wide enough. Then we can see the average member in each cluster as and what are their sort of coordinates in the original variables. This is the center of cluster 1, this is the center of cluster 2, and this is the center of cluster 3. So we know that all data cases who are member of group 1, the 53 here, they must be sort of similar to this one in a sense, right? And now we can look at the different variables to see what separates the groups really. And we can perhaps see that this internode and petals and internode, these 2 variables here, are sort of different between the groups, while perhaps some other variables are less different, right? For instance, this last one here is sort of similar between all the 3 groups, so it doesn't really distinguish very much. The last output is this total within sum of square that we talked about. That was minimized. So this is the minimized value for this one now. We will come back to this later. That's why I show it. Let's do the PAM as an alternative to k-means. And let me copy this code. So here we need an extra R package called cluster. So let me load that first, like that. And then you can see the command is sort of similar, but with some important differences. Now we supply the distances, right? Not the data themselves, but you must have computed some distances, or it's not like you must, because you can also supply the data here. But typically we do this when we want to compute some distances on our own. And now I use the Manhattan distances instead of the Euclidean, right? Just to show that this will work. Instead of centers equals 3, it's called k equals 3. And n start is the same. So this is also, for this exact same reason, we should restart it several times. So let's run this one, and it's super fast as well. And we get an object with slightly different information inside it. If we look at the PM here, you can see it has some differences. And let's have a look at it. First of all, this is the clustering vector again. So this is, it's just called clustering instead of cluster. It's the same type of information, right? This gives you which group each data case belongs to now. And we can always look at this table. If I, it's now CLS PAM, and it's called clustering. Yeah, split into slightly, and please remember that group number 1 here may have nothing to do with group number 1 in the previous, in the k-means, right? Which group is number 1 and 2 and 3? That's pretty random, right? So it could be that the group 1 here is the same as group 2 up here, right? Because it's probably more or less the same, right? Because it's, you look at the sizes, but they will not be identical anyway, especially when we change the from Euclidean to Manhattan distance. Instead of the centroids, you of course now have the medoids, and instead of listing their values, you just list which ones are the medoids, and then you can go and look up in the dataset yourself. Row number 61, 28, and 45, right? Those are the medoid rows now. And then this plus info here is a table where you have some information about each cluster. First of all, the sizes, that's the same as we did here. How many members do you have in each cluster? And here you have the maximum dissimilarity, the average dissimilarity, right? This is actually this this is the criterion that is minimized, right? Some of these. And here you have some diameter and separation and so on in each group. You can read about this in the help file if you like. You can see the size of each group here, if they are very different from each other. Typically a small group will be smaller diameter, right? So this is how we do partitioning, straightforward, but please remember this STAT. Let's see how we can do partitioning in R using k-means and then PAM. So first of all, let me copy this code here into our studio like this. And actually the k-means function is super simple. It's one line of code like this. It's always available in R. You don't need any extra packages. The first input is always the data, the raw data. And now I have to remember that up here I added this extra column to my taxa data, right? So actually if we have a look at that data set now, I should not include this last column here, right? This is actually not part of our data. It's the first 7 columns who are the data, right? So let me while I remember it, go back here and specify that I should look at only column 1 to 7. Otherwise, I will also include this column here as a data column, and this will of course affect my results. So that would be silly. So I should keep that out of my data set now. Yeah. So you have to do this. It will still work if you don't, but you will get a result that is also influenced by the cluster. The clustering result from the hierarchical clustering will sort of be a data column. That's silly. Okay, we can do the clustering like this. Zap, it takes virtually no time. And let's have a look at the content of this object here, cls.km. If you click it open like this, you will see that it contains some objects inside, and we will have a look at some of them. The first one is this, the cluster object. And this is the clustering information like we saw with the hierarchical clustering when we cut the dendrogram. So here we have now each data case, right? Data case 1, 2, 3, 4, and so on. And here is the group they belong to. Group number 2, group number 3, 3, 3, group number 1, 1, and 3 again, and so on. So it's the same type of information. A cluster vector, we call it. That with integers indicating if you are belong to group number 1, 2, or 3. We can, of course, do this table like we did previously, just to see how many are in each group. And here we chose 3 groups, right? So we have 3 groups, 53, 39, and 28 members. None of them are particularly small, which is good. It's if you get a super small group and only have 3 groups, then it's probably some outliers or some very deviating data, right? Notice we also use 10 restarts here. Always use more than one, I would say. How many? It's super fast, so you can easily use more than 10, but at least 10 or at least some, right? Okay, that's the clusters. We can also have a look at actually the centers in each cluster. So if we make that window a little bit, yeah, we can do, yeah, that's wide enough. Then we can see the average member in each cluster as and what are their sort of coordinates in the original variables. This is the center of cluster 1, this is the center of cluster 2, and this is the center of cluster 3. So we know that all data cases who are member of group 1, the 53 here, they must be sort of similar to this one in a sense, right? And now we can look at the different variables to see what separates the groups really. And we can perhaps see that this internode and petals and internode, these 2 variables here, are sort of different between the groups, while perhaps some other variables are less different, right? For instance, this last one here is sort of similar between all the 3 groups, so it doesn't really distinguish very much. The last output is this total within sum of square that we talked about. That was minimized. So this is the minimized value for this one now. We will come back to this later. That's why I show it. Let's do the PAM as an alternative to k-means. And let me copy this code. So here we need an extra R package called cluster. So let me load that first, like that. And then you can see the command is sort of similar, but with some important differences. Now we supply the distances, right? Not the data themselves, but you must have computed some distances, or it's not like you must, because you can also supply the data here. But typically we do this when we want to compute some distances on our own. And now I use the Manhattan distances instead of the Euclidean, right? Just to show that this will work. Instead of centers equals 3, it's called k equals 3. And n start is the same. So this is also, for this exact same reason, we should restart it several times. So let's run this one. And it's super fast as well. And we get an object with slightly different information inside it. If we look at the PM here, you can see it has some differences. And let's have a look at it. First of all, this is the clustering vector again. So this is, it's just called clustering instead of cluster. It's the same type of information, right? This gives you which group each data case belongs to now. And we can always look at this table. If it's now CLS PAM and it's called clustering. Yeah, split into slightly, and please remember that group number 1 here may have nothing to do with group number 1 in the k-means, right? Which group is number 1 and 2 and 3? That's pretty random, right? So it could be that the group 1 here is the same as group 2 up here, right? Because it's probably more or less the same, right? Because it's You look at the sizes, but they will not be identical anyway, especially when we change the from Euclidean to Manhattan distance. Instead of the centroids, you of course now have the medoids, and instead of listing their values, you just list which ones are the medoids, and then you can go and look up in the dataset yourself. Row number 61, 28, and 45. Right? Those are the medoid rows now. And then this plus info here is a table where you have some information about each cluster. First of all, the sizes, that's the same as we did here. How many members do you have in each cluster? And here you have the maximum dissimilarity, the average dissimilarity. Right? This is actually this this is the criterion that is minimized, right? Some of these. And here you have some diameter and separation and so on in each group. You can read about this in the help file if you like. You can see the size of each group here, if they are very different from each other. Typically a small group will be smaller diameter, right? So this is how we do partitioning, straightforward, but please remember this end start. Let us finish by considering how many clusters we should use. And this is typically where in the dendrogram do we cut, or at which k in the k-means or PAM do we sort of stop, or which k do we choose, right? And first of all, clustering is explorative, so don't be afraid to explore, right? It's not like you have to do the computation we will see now, because it's explorative. But in some cases, it could be nice to have an sort of objective computations that support the choice of clusters in one way or another. So what do the data support actually, right? That's what we are trying to look at now, because otherwise it's very subjective, this, right? And I will look at one criterion. There are more than one. This is called the gap statistic. Yeah, I think it's one of the most considered one of the sort of best, in a sense, criteria, but there are some other criteria that you might look at. Let's look at the gap statistic idea. What is the idea? And here I have some data that really illustrates this idea. To the left here, I have a data set where we immediately, only by visual inspection, see that here we have actually 4 groups, right? This is p equals 2, so it's only 2-dimensional. We can plot everything, right? And we can immediately see the grouping. So we didn't really need to do any clustering to see that this is 4 groups, right? But we will use this now, because here we know what should be the outcomes, right? What I have on the right hand side here is, it said simulated, right? What is this? When we are going to look for grouping in our data, we have to sort of compare it to something which is not grouped. And this is actually a random sample of data in the same sort of region. Can you see that? If you look at how this axis spans the values, right, from 8 to like 25 or something like here, and the same here, 8 to 20, it's almost the same, right? So this covers the sort of the same region in the data space as our real data do. But here, instead of being grouped, everything is just randomly selected uniformly. Uniform. So all values are equally likely inside here, right? And then you just sample a data set of the same size as this one, right? And it looks like this for the random sample. Of course, when you do this random sampling over and over again, they will look different. But there will be no grouping in this data, right? They will come out randomly. What we do then is to compute the sum of squares within each cluster. right? So here we now have actually just one cluster. We haven't clustered anything, so everything is one big cluster. And we compute this sum of squares again, right? Like the k-means did. And since we have only one cluster, k equals 1, okay, we compute the sum of square, of course, inside each group here, but now we also need to compute across groups, right? Because, or actually, everything is one group now, both here and here. And then we get this within sum of squares for the real data to the left and for the simulated data to the right. And they are, yeah, more or less of the same magnitude, actually bigger here, right? Because data are sort of clumped in the corners. While here you have smeared more. If everything was in the center, it would be sort of smaller values here. But anyway, we start out like this, with k equals 1. One single group, no clustering of any kind. Compute this. Then we increase the number of groups. And what happens? Here I have started to cluster into two groups. And we can see that the real data clusters into two groups like this, the blue group here and the red here. The simulated data like this, red and blue. And now we can compute the same within each group and sum over groups, right? And now you can see the values are smaller, of course, in both cases. Both here and here, groups have become sort of smaller, right? Because there are two of them, really. So both of them drop, but still we can see that they are more or less of the same magnitude, and this one is still a little bit bigger than this one. Then we increase to 3 groups, and it looks like this: red, blue, and green here, red, blue, and green over here. And again, we can compute this within sum of squares, and the values get smaller again. But still, we can see they are more or less in the same relation, right? This one is slightly bigger than this one. And now we split it into 4 groups. And now look what happens, right? Because now we have exactly the 4 groups that these data sort of invites us to have, right? While over here, the 4 groups are a little bit sort of all over the place. And now when we compute the within sum of square, we have this sharp drop here. Can you see that? Sharp drop. This drops to almost 10 times as small as this one now. This one also drops compared to the previous ones, but this one drops super much. And this is exactly the idea behind the gap statistic. Because the gap is now simply, if we plot this, the values that we now saw, for one cluster, we have this within sum of squares, right? For the two, for the real and the simulated data, almost the same. The real a little bit more than the simulated. Then we increase to to 2 clusters. Both of them drops, but they drop approximately the same. Then we increase to 3 clusters. Again, both of them drop, but approximately to the same, equally much. But here you see the big drop in the red one. And notice what happens after here. When we start to clustering into 5, 6, 7, then these 2 curves are more or less parallel again. Can you see that? Because splitting even further now does not give us more than this steady decay in both cases. And the gap is actually the difference between the blue and the red curve here now. So the difference here, and it's also a log transform of this value. Yeah, so actually we have on this scale here already log transformed the values we saw previously. So it's the log within sum of squares that we compare to each other. And the first time we see a big gap is the proper K. That's sort of the idea. And this blue is now, in this case, it's based on one single simulation. That's why it's a little bit up and down here. If you use many simulations, you will get a smoother blue curve, and you will also get some standard errors on the bars you could imagine on the blue one here. And that should also be taken into consideration because the gap must really be bigger than the standard deviation to be a sort of significant gap in a sense. Yeah, we can always have a look in R and how to compute this gap statistic, but here is the idea, right? That as long as the data, if the data are sort of uniform distributed, no grouping at all, it should drop according to the blue curve. If you see a dramatic drop more than the blue curve, it indicates that here you have stumbled across a division in the data that is really supported by the data. So we should actually stop here then, because you see going further here, there is no more drops. Let's go and see how we do this in R. So let's turn to R again and see how we can do this, compute this gap statistic. And actually it's a function called clustergap in that cluster package that we mentioned previously. So you don't, if you have loaded this one, you don't need anything more. First thing we need to do is to make a function. Let me just copy this. And what is this? Let me put it here. You need to make a function, and this is sort of similar to the bootstrapping we did last week, where we also had to make a function where the first argument is the data that you are going to cluster, and the second argument is the number of clusters you want to have. And then inside here, you decide how to cluster your data, right? So in this case, I compute a distance matrix using Euclidean distances, and then I use the PAM to do the clustering into K groups, right? Based on this distance object here. But of course here, these two lines you can now replace with whatever you like to do clustering. You can replace it with K-means, or you can replace with some other distance metric here. You can actually also do hierarchical clustering. Then you do the distance computation, then H cluster here instead of PAM. And then you need the cut tree as well, right? And cut into K clusters and return. Because the output from this function should be that clustering vector in a sense. Or an object that contains such a vector. Okay, that's the first thing. Then we need the line here to do the actual gap statistic. And now you can see we supply the data. And now again, well, I have to remember now, I don't want to use that. I only want to use the first 7 columns for, that's my data, right, in that table. Here we supply this function now, right? So this cluster gap will call our function and make use of it. And we specify the maximum number of clusters that we want to try out. Because, and here we say 10, so it means we will try 1, 2, 3, 4, up to 10 different clusters. The last one here is the number of bootstrap samples, the number of simulations, as we saw in the lecture. I called it simulations, and that's what it is. It's called bootstrap samples. It's sort of a bootstrapping this, because you simulate 50 of these uniform random data sets to compare your real clustering to. So let's run this, and first we have to run sort of the function here to register the function, so it's available. Here it is now as a function, and then we can use this here. And this will take a little bit time because it has to do this 50 times, right? So it will count here. That's why I choose only 50. You will probably use more than 50, I would say, 100 or something like that simulations, but take some time, so I stopped at 50 just to make it doable within a reasonable time. There it was 50. So now we have this GS object here. It's a list of 6 different objects inside, and let's have a look at this object here called tab. because that's really the important one in a sense. It's actually just a small table where this is the number of clusters in a row. So from 1 to 10 clusters, right? And here we can now see the within cluster distances for the real data in this column. This is for the simulated data in this column. And here we see the gap between them. And it looks like the gap is not very big. It looks like it's more or less the same. Can you see that? It's not a super big gap anywhere here. It stays the same more or less all the way through, I would say. And also this standard error here should be taken into consideration, right, when you compare the gaps to each other. Actually, we don't typically sit and look at these outputs like we do now. I do it just to show you where they are, because we typically use this function here to get an idea of where to stop. It's called max SA, this function, and you see that we supply as input these two columns here. These two columns, gap, and these two last columns here. Yeah, these are supplied as input to this function. It's part of the same package. And then there are some methods to choose where to stop. Where should you stop, right? And here, this is, I think it's the default. You can read a little bit about this in the help file for this function. Question mark max SA, like this. And here you find the help file for it, and here it will list these ways of choosing this method, right? Option. Global max simply corresponds to the global maximum, the biggest gap you find anywhere along the number of clusters, right? Or you use the first maximum and disregard everything about the standard errors. This is from the original paper by Robert Tibshirani that introduced this method in 2001, and he had a criterion there that you can choose. The smallest case such that, yeah, blah, blah, blah. You can read about the details here. This is the default. First SA max, first value not smaller than the first local maximum, yeah, minus blah, blah, blah. Or the global. Yeah, there are some options here that will turn out, especially the first two ones here will tend to give you many clusters, I think, while all the others tend to give rather few clusters. Let's see what turned out here. If we run this, 2, it says. 2 cluster is optimal for this data. So this, and we can see, we can actually see it from here, right? That here we have the biggest gap. It increases from 0.17 to 0.22, and then it doesn't really increase anymore at all. Or it could actually increase a little bit more, but since we use this first SE max, we will typically stop at the first time we see a maximum, yeah, local maximum. So in this case, the data supported split into 2 groups. We can actually plot. I just made some code here. It's not super important. You can do it if you like. It's sort of a lot of code in a sense, but for making a plot of this. And here you can see it, right? That here we have now the drop in the real simulated, sorry, the real data, and here are the simulated ones. They are bigger, right? But we can see that the biggest difference is here at 2. And here we also have this standard error in the. So this is significantly smaller than this one all the way through, actually. And that, of course, depends on the data and also on the metric a little bit. But here was the first maximum gap. Okay, that's the gap statistic.